Okay, welcome to week 5 in review. Week 5 was essentially all about electrolytic cells. So week 5, um, electrolysis, electrolysis or electrolysis. So electrolysis is a compound word. It's made up of essentially electricity or electrons. So electricity, and then lysis, which is a word which means to split. So essentially electrolysis is using electric current to split an ionic compound which otherwise wouldn't want to separate. The first thing I did then, which seemed like the logical thing to do with lessons, was to compare and contrast an electrolytic cell versus an electrochemical cell. So electrochemical cell versus an electrolytic cell was what I started the course off with. So if I scroll down a little bit, so electrochemical versus electrolytic. Now, first of all, we just start by drawing a general diagram of each of the cells. If I just take this color here for electrochemical. Okay, so electrochemical cell, you have two half cells. So two half cells, and within each half cell you have an electrode. So on the left-hand side it's called the anode. Then typically you put a voltmeter within the circuit, and then on the right-hand side the electrode is called the cathode. There's also an electrolyte or an ionic solution in each of the half cells, and then to bridge that gap between both half cells you have a salt bridge. So that's your salt bridge. So that's a typical electrochemical cell, whereas with an electrolytic cell you're going to have just one container. You still have both electrodes, so on the left-hand side it's still called the anode, and then on the right-hand side it's still called the cathode, but up here where the voltmeter normally would be, you now have an external power supply, for example a battery or a power pack. And both the electrodes are still immersed in an electrolyte. So what we're going to do now is we're just going to do a simple compare and contrast. So if we start off with the electrochemical cell, with an electrochemical cell you have two half cells. Two half cells are simply containers. So those containers, if you're doing it in a school lab, will typically be a beaker. So two half cells. Whereas in an electrolytic cell you have just one cell or container. Right, the next difference to point out is that because of the two half cells in an electrochemical cell, you need a salt bridge. Whereas in an electrolytic cell, because there is only one cell, there's no salt bridge. Okay, the next thing to point out is that the reaction which occurs in an electrochemical cell is spontaneous. So you get a positive E cell value if you added the two individual reduction potentials together for the species involved. So it's a spontaneous redox reaction. And whereas in an electrolytic cell, this is a non-spontaneous redox reaction. Now, as a result of this point, because the electrochemical cell has a spontaneous redox reaction, there's no external power supply needed. No external power supply needed. Whereas with an electrolytic cell, because this is a non-spontaneous reaction and essentially nothing will occur, then you must use an external power supply. An external power supply, and that external power supply is present in the form of a battery there. Let's scroll on down a little bit more. Other things we can point out here is that in an electrochemical cell, oxidation occurs at the anode, and the anode in an electrochemical cell is negative. So we put that negative in now. So oxidation occurs there. Now oxidation also occurs at the anode in an electrolytic cell, but the anode in an electrolytic cell is positive. So if you just remember that the charges on the anodes and the cathodes are opposite. That's one of the main differences. So the anode here is positive. And then on the same note then, reduction occurs at the cathode in an electrochemical cell. Its charge is positive. Reduction also occurs at the cathode in an electrolytic cell, but its charge is negative. So that's a difference there. So positive versus negative. Just one last point then to finish this compare and contrast. Electron flow is from the left-hand side to the right-hand side in an electrochemical cell, and also electron flow is from left-hand side to right-hand side in an electrolytic cell. So that is an extensive compare and contrast between an electrochemical cell and an electrolytic cell. So the main thing is, do not mix the two processes up. Now the next thing I did was, after the theory lesson, we decided to take a look at some practical applications of electrolysis. And as I said already, electrolysis is typically used to split up ionic compounds which otherwise wouldn't undergo redox reactions spontaneously. So examples of some compounds which are split using electrolysis would be lead bromide, sodium chloride, and copper chloride. Now if I focus on copper chloride, because that's the species that we studied during our class practical, and you can see some pictures of the evidence of that on Facebook, which is quite cool. Let's just talk about copper chloride and the electrolysis of it. So, electrolysis of copper chloride. Electrolysis or electrolysis of copper chloride, which is a turquoisey blue solution. Okay, so the cell that we had would have been like this, just one container. You had your anode on the left-hand side. We hooked it up to a power pack. 6 volts was the voltage that we were using, and then we had a cathode here. Both the electrodes were made of carbon. This was carbon solid electrode, anode and cathode. And then the electrolyte was like I say, a turquoisey colored copper chloride solution. So that was your essential setup for the experiment. And then what we needed to discuss was the redox chemistry which was taking place once this 6 volts power was supplied. So the first thing we want to talk about is oxidation. So oxidation at the anode. Okay. Now, I'm getting ahead of myself, so I'm just going to delete that for a second. I need to talk about the 2 ions which are present in copper chloride. So the 2 ions which are present in copper chloride are Cu2+, and you have 2 chloride ions for every copper 2+ ion. So the situation with electrolysis is that the anion will move to the anode, and the anode is positive, and the cation will move to the cathode. And this is similar to how the ions from a salt bridge move in an electrochemical cell. So if the cation moves to the cathode, that makes the cathode negative. So what we want to talk about now is what happens to these ions when they move to their respective electrodes. So if I just start with oxidation at the anode, and make sure I have a thin pen. So oxidation occurs at the anode as follows. So you're oxidizing your chloride ions, so you have Cl- going to Cl2 gas. You want 2 of those there. You want to balance your charges, so you have 2 electrons here, which is your oxidation. So that's your equation for what happens at the anode. Oxidation at the anode, and then at the cathode, the situation you have is reduction. So reduction at the cathode. So what we have is reduction of Cu2+ cations going to copper solid. Okay, and that's a reduction. So the only other thing to really talk about here is the appearance of any species, or the detection of any species that form during these redox reactions. So with the chlorine gas, essentially if you just put your nose about this close to the, that's an interesting drawing. If you put your nose about that close to the electrolytic cell, you would have got a smell of chlorine gas. Smells very like a swimming pool. And then on your cathode, you would have had a build-up of copper solid on the cathode. And then the last thing that we need to discuss is some applications of this process. So if I just scroll up here a bit just to give myself some space, some applications of electrolysis. Right, here we go. So the first one here, you can have electro plating is what it's called, electro plating. So in lesson we electroplated a pencil sharpener, we electroplated the pen, and there's evidence of that on Facebook. You can take a look at the pictures. We electroplated some coins. So electroplating, quite useful. So all the copper coins that we have in circulation in New Zealand, it would be uneconomical if we made them out of solid copper. So what you use is a base metal like zinc solid, and then you copper plate it with some copper, and that's more economical. Other applications of electrolysis, you can have, sorry, I'm running out a wee bit of space here, I'll just do it over here as well. You can electrolyze aluminium oxide, so Al2O3, and you can separate out the aluminium solid. Multi-billion-dollar industry, because as we all know, there's so many window frames and door frames and other products made out of aluminium. So that's another example of electrolysis. You can also take sodium chloride, molten sodium chloride, and you can electrolyze that so that you can free up the solid sodium, and again chlorine gas. So there are multiple applications of electrolysis, and essentially you use it when the reaction would otherwise be non-spontaneous. So that kind of brought the redox course to completion. It's a case now of the only other redox chemistry we're going to come across is the redox chemistry, which is relative to any redox titrations that you guys may be carrying out for your extended practical. But otherwise, that, as it stands, that is your redox internal course completed. So please provide feedback on these videos, and there'll be another series for the next topic that we cover.